Hi, everyone. Thank you very much for being here this afternoon. Really excited to be part of this conference. I hope you're as well. It's been a blast so far. So let's start with a quick survey just to get a gist of who do we have in the room. Who knows about Reactive Streams in the audience? There you go. How about Akka Streams? Bunch of hands. That's good. So these things have definitely boomed, right? So there's still a constant buzz about these great pieces of tech that we can now rely upon. And whenever you need to build, handle potentially infinite streams of live data with no predetermined volumes, reactive streams are definitely the answer, right? And by employing like asynchrony and back pressure, they allow you to build elastic and resilient data pipelines. It's very easy as well to get started with them. So you can easily start experimenting and playing around with Akka Streams, for example. That's one of the implementations, as you know. And again, there's plenty of examples online. Documentation is great. But at some point, it's likely that you'd like to move forward from here, right? So you'd like to move forward to build battle-ready, production-grade systems with this tooling. And this step is not always easy. And it's what we'll focus on, actually, in this talk. And it's a common situation. So I've personally found myself in this situation more than once, and not just with software. So you start building something simple, and you succeed, and you're so excited about it. Behold the miracle here. But when it's time to move forward and build something bigger, it can bring agony and despair sometimes. And this is because you need an additional set of tools and knowledge to deal with the issue. Now, this is because very simple examples are good at helping you grasping the concepts, of course, but they don't get you very far when you're building a whole system. So this talk will try and offer an approach and a few patterns to design and implement production-grade pipelines with Akka Streams. This is me, on the left of the slide. My name is Stefano. I work for HomeAway in London, UK. HomeAway is a brand of the Expedia Group, if you don't know it already, that focuses on the vacation rental market. And it's also headquartered in Austin, by the way. So here's what I'm going to do. In the first part of the talk, I'm going to introduce you to one of the problems that we faced at HomeAway, and that's going to serve as an example to present our approach to design and implement production-grade pipelines with Akka Streams. So here's our problem. HomeAway currently is on a quest to assert their presence on the vacation rental market. And what we're specifically interested in is digital marketing automation. The goals of digital marketing automations are two. First one, of course, is automating repetitive actions that are traditionally performed by humans in the digital marketing sphere. And second goal is to move forward and gain an edge over this human activity by minimizing errors and reaction times. So essentially, we want something like this. So we want to make our advertisement more effective, and we want to make it dynamic, right? So we want to show relevant content to the relevant people at the relevant time. So let's assume someone was on homeaway.com, for instance, earlier today, and was looking at this property, like reasonably priced villa in South Africa, but didn't book it, right? So it would be a very good target for us to show an ad like this to try and bring him or her back to the site to complete the purchase. Now, the key point here is that whoever displays this ad needs to know about HomeAway's data, right? And the data of our properties. And this data can change a lot. It might seem static, but for example, the price of the property might fluctuate a lot. And for this advertisement strategy to be effective, we need the advertisement platforms to be in sync with our data. We need to get our data there, and we need to get it there as fast as we can. So this operation of sending product data to advertisement platforms is traditionally done manually by human marketers, sending big, chunky Excel files to some email address somewhere, hoping no one on the other side is on holiday, and that simply does not scale. What we want is automate this, right? Make this programmatic. So essentially, we want to set up automated data feeds from us to these platforms. So this seems easy, but first of all, there are multiple platforms we might want to reach. So what you can see here is just a bunch of them. It's not a whole lot. They want different data, presented differently, and they support different integrations. Second, the information we might need to send could be scattered among many places within HomeAway. We've got a variety of sources that we need to integrate. These could be, Kafka feeds, REST APIs, whatever. So the problem is growing already. So to tackle this, essentially, we need a pattern to enable a quick rollout of pipeline applications, which are, first of all, resilient, as they need to be always on, recover from failure, keep pumping data to these platforms, and we need them to be scalable. So we need to, of course, handle changing and potentially increase in load. So in other words, we want our feeds to be reactive. And indeed, Reactive Streams is what we went for solving this issue. So as you probably understood, our tool of choice is Akka Streams here, our implementation of reference. But instead of focusing on the benefits of choosing, leveraging as well Reactive Streams and Akka Streams to protect the resiliency of your systems, I'm going to assume this discussion has already happened in your team. And you're now moving forward and tackling the following problem. How do I build a production-grade system with Akka Streams? So for the purpose of this talk, I'm just going to simplify the problem that I just mentioned and use it as an example. So let's assume we want to build the following reactive pipeline. We have a feed of property data that is changes in our properties. And we want to validate, process this data, and send it to Google AdWords on the right-hand side, right? So these are the integrations. We have a Kafka feed we consume from, and we want to talk to AdWords using its HTTP web API. So this is actually a simplified view of the AdWords feed we got running in production right now. So we set out the problem. Let's see how we can go about it. So we're going to touch on three main aspects of developing a pipeline with Akka Streams. We're going to lay out the stages of our pipeline. Then we're going to design the types of these stages and let this guide the implementation of our system. And we're going to see some code for that. So first step, we want to break down our pipeline into stages, right? So first of all, what is a stage? So this term is borrowed from Akka Streams lingo. And it's essentially a reactive component of arbitrary complexity. It's reusable and composable. It comes in form of source, flows, and sink, depending on the shape the stage has. And that is the number of input and output ports that it has. Now, it's important to note here that, to us, these are just not Akka Streams DSL objects. They became part of our ubiquitous language. In other words, they became the official glossary used within the team when discussing pipeline design problems. Now, stages have great composability, as I mentioned. So this means that you can connect an output port of a stage with an input port of another stage and obtain a new stage with a new shape, right? So this is fairly trivial in the examples I've presented here. So for example, you can just take a source, connect it to a flow. You will end up with a new source because the stage that you obtain will still have one output port, right? Now, a special case is a runnable graph that you see in the last two examples. So you get one of those when you have connected all the ports in your stages. And this means that no input and no output ports are available anymore. And this kind of stage that can be run in Akka Streams, you can actually call a run method on it. In other words, that means that you feed the the graph to the Akka Streams infrastructure and start pumping the data through it. Now, the composability rules you see here tell you something very important, that you should, you can and you should start simple when designing your pipeline. You start by designing it with very few simple stages, and then if needed, you can incrementally deep dive into them to handle the complexity. And getting your abstraction layers right is particularly important when the pipeline grows in complexity. So with this in mind, let's go back to our example and try to identify the stages here. So here are the integrations. So we've got Kafka and our HTTP interface. So the first step is to set up a source for any integration that consumes data and a sink for any integration that produces data, right? So this is the easy part. Now, what happens in the middle? So anything could happen here, right? So there could be something massively complex or something trivial, anything in between, right? So keeping in mind, we want to start simple because we still have to tackle the complexity inside. We have to envision this as a single flow that masks all the complexity that goes on underneath. So this is what we start with. We just put a flow between our source and the sink, right? Now, the last part is that everything will be wrapped by a runnable graph. And this is something you're always going to need if you actually want to run data through your pipeline, which I guess is what you want in the end, right? So this is our first cut stage split. Now, let's try and move to the next step. And this is identifying the stage types. We found it's very good practice to think, brainstorm about these types, and let them drive your code. So an Akka stage has a type signature, right? Here you can see, for example, the signature of a flow. So this is Scala syntax, but Java, of course, doesn't really change. So going from left to right, you're going to see the types of the stage ports, right? So each port is strongly typed, so it's going to have a type. And in case of a flow, we have two ports, one input and one output, so we see two types here, right? Now, the last type, and the only type every stage is guaranteed to have, is the type of the stage materialized value. And the materialized value is something that Akka Streams gives you back when you run a stage as part of a graph. So from a practical point of view, it's basically your chance to interact with a stage after it's running. So say you want to be able to interrupt the flow of data. You can expose here something like a stoppable object or an interface, something you can call stop on. There is also the possibility that a stage doesn't need to expose any interaction handles. And for this purpose, Akka Streams defines something like an object called not used, which makes it clear from whoever looks at the types of the stages that the materialized value for this stage is not meaningful. It can't be used. It can safely be discarded, essentially. So let's now move back to our example and think about the types here, right? So our source will be a source of properties, or better, a source of property changes. So as Jonas mentioned yesterday as well, it's good to think about events here instead of entities. So we're going to start with a source of property change, and our materialized value here will be not used. Why is that? Now, this is because in our specific example, we want our pipeline to be always on. We want it to be an infinite stream, right? So we don't really want to manifest any intention of anything interacting with it from the outside. Now, of course, if you want to, if your requirement changes, you want to manage the lifecycle of your source, and for example, be able to shut it down from outside, like you want to expose something like, again, a stoppable object or shutdownable or whatever here. So in the flow, we're going to ingest property changes, and we will produce something like a new event that we might call AdWords change, for instance. Like this is the transform data that we want to push forward to Google AdWords. So on the sync side, we'll be ingesting these changes. So it's going to be a sync of AdWords change. And here, it's a good idea to expose something as materialized value. This is a feature that we can listen to for the completion or failure of our pipeline. Now, one might argue if the pipeline should be always on, there's no need for that. But it's actually good practice to put something here in case something goes wrong. And it's actually good to keep listening to this feature anyway. So finally, the graph that's wrapping all of this. Again, it doesn't have any ports, so it will only have one type, which is the materialized value, right? So this will reflect anything interesting that is materialized in the stages inside. So as we've seen, the only interesting thing that we've materialized comes from the sync, right? So what we do here is we bubble up this feature to the graph layer. So it seems we have an end-to-end pipeline with our types. Now, the million-dollar question is, like, would you go to production with a pipeline like this? So suppose we ingest, for example, a property change which is not valid, right? And we cannot produce an AdWords change out of it in this case. What's going to happen here? We don't know, right? It's not clear looking at these types. It's not clear what the system will do in case of errors. So the key exercise here is to try and hunt down the side effects that might happen in your productionized pipeline. So consider all the things that could be handled as side effects in a productionized application. So we just mentioned error handling, there's logging as well, there's monitoring. All of these things, the key step is to convert them into regular events flowing through your pipeline. And the Reactive manifesto itself, it suggests to treat errors as events because it allows to keep processing our stream of data with no special action or interruption. So the error just gets propagated downstream just like any other message. And this is not just valid for errors. So you can do the same for any like audit, message, or logging, or whatever you want to record in your system, right? So when designing our stage types, essentially this translates to more complex expressive types, right? That make our stages completely transparent from the outside. We might even talk about preferentially transparent stages in a way. So these are on the slide, you see a couple of examples of such types. So the first one, for example, is a flow that can produce either an error or a valid result, for instance. So if you work with Java, there's more than one good library you can use that you get either type from, like Lambda here, or functional Java. If you work with Scala, of course, it comes for free. The second type you can see in this example is essentially a flow that produces always a result, which is the out type. And it also produces a bunch of events, for example, with it. This might explain, for instance, how this value was calculated. It might come like as an added audit information. So there is no silver bullet to nail the type to use, of course. Like each stage semantics must be analyzed in order to nail the right type here. So from now on, I'm going to focus on the error handling case, but the same rationale can be applied to audit, for instance, or logging as well. So keep that in mind. So going back to our example here, our flow can be changed, right, to produce either an error, like a validation error, or an AdWords change. So this enables separation of concerns downstream, where we can handle errors in one sync and valid AdWords changes in another one. But clearly, errors are not bound to happen only in the validation flow. So we could have errors, for example, while talking to AdWords, for instance. So we need a way to generify this behavior. And a way to do this is to use another flow to model the AdWords storing logic, which can now produce either an error or a positive signal, for instance, which we can call stored, right? So this is the same pattern we used previously. So if we do this, we can now envision like a single sink that handle all the errors if we arrange these errors in a hierarchy, for example. And this makes it very convenient because we can now handle all the errors in one place. So this is our first cut graph topology, say. So let's assume we're happy with that. We have all the types laid out. We can now let this drive our implementation, right? So the examples I'm going to show are mainly in Scala, but there's nothing magic about them. So it's mostly Akka Streams DSL, which is available in Java pretty much the same form, minus some verbosity, I guess. So let's go back to our graph topology for a second and start implementing the stages one by one. So we can start from the source. So the first thing that we remind ourselves, so we already decided the type. So it's going to be a source of property change that materializes to a not used. So finally, let's see some code, right? So the types I just mentioned, you can see them there. It's a good point to start from. So now it is actually a good moment before we start bashing code around to look for any library which might already offer what we need. And this is indeed one of the key strengths of Akka Streams. Now the community is going berserk around Akka Streams and it's providing all sorts of connectors and integrations that you can pick and choose from. So Alpaca, for example, is a great example of such libraries. So especially for integration stages, it makes a lot of sense to check what the community can provide for you. And of course, feedback to the community. So in our case, we need a source that reads from Kafka, right? So in this case, it makes a lot of sense to use Reactive Kafka. So this is a stable library that can give you sources and sinks to interact with Kafka topics. In this example, you can see how you can easily get a Kafka source by providing a bunch of settings. Now, the settings part, it's been omitted here to make it a bit clearer. And that's going to be something you need to provide the deserialization logic, of course. But hopefully you got the gist of how easy it is to get a source from this library. It's essentially one main call. It's this consumer.plain-source. The catch here is that the source you get back from Reactive Kafka does not have the type you want, right? So I've exploded the types here. You can see it's a source of consumer record that materializes to a control handle, right? So these are not the types we want, of course. These are Reactive Kafka specific types. We don't want to leak them outside of our stage. We want our own types we already decided, right? So what we go on and do in the second part of this stage is we use map and map materialized value. These are combinators that Akka Streams provide to adapt what we get from the library to our own domain types, right? So if we go on to the processing flow, this is a different story, right? So it's definitely not something we can find off the shelf, of course, like the Kafka source. So this, we need to take care of the logic ourselves here. So here's the type we need to fulfill, property change in input, and we produce an either, right? So the idea here is that the custom stages like this need to be wrappers around domain logic, right? So this is why we can go ahead and define a service class. We can call it with lots of creativity, like property processing service, for instance. And this is going to be performing the processing duties, right? So assuming, for example, in this case, that the validation we need is CPU bound, we can use something like flow.from function here to wrap calls into flows. And this is essentially going to be delegating the business logic to our domain module. Now, this guarantees a clean separation between your reactive stage and your business logic. It helps code readability and testability. So it's a sensible thing to do. Now, if the complexity of this stage increases, as we mentioned previously, we can add further abstraction layers by keeping this flow signature intact, right? So suppose we want to split the processing into steps. We want to do some validation first, and then some transformation, right? One thing that we could do, for instance, is we could delegate these two operations to two different domain services, and the flow can be obtained by concatenating them using map, right? So this is easy. The only catch we need to keep in mind here is that when you deal with fully synchronous calls like these ones, if you concatenate more than one, Akka Streams will treat them as one stage. So essentially, it will smash them together, and pipelining will be disabled across the whole section of your stream. This could become a bottleneck in some cases. So what you could do is you can actually tell Akka to run them separately. So you can force what's called an asynchronous boundaries between them to actually say run one stage in a separate context from what follows it, right? And this you can do by adding this async combinator between these two stages. So moving to the AdWords flow, this is equally simple. It follows the same thought process. It wraps another domain service that we can define here. We can call it AdWords service. Now, the difference here is that this will go and talk to Google AdWords over the network, right? So it will be I/O bound. Hence, it will provide an asynchronous behavior. We are going to use map async here, as opposed to from function that we used before. So this combinator take a parallelism factor, as you can see from the code. We take it from a config object we just passed in. And this essentially we can use to limit the number of parallel calls that we can make to Google AdWords. So again, it's important to notice here that the separation between the reactive logic, that is the parallelism management via the map async, and the actual business logic, which is delegated to our service.store call. As for the error sync, now you probably got the gist of this by now. We can create another service that handle errors, and this can be wrapped by a sync using, in this case, sync.forEach, right? Note that once more, we make use of the map materialize value construct here to discard the materialized value of the sync for each, which would be a future. And this is because we want to make it transparent from the outside that we don't need any interaction with this sync, so we expose a not used handle here. So the graph is where everything comes together again. So let's just take a look at how it translates in code. So types first. This is going to be a runnable graph that materializes to a future, right? Cool. So first of all, we're going to need all the stages that we implemented previously here in order to build this graph. So these are all, we've got 4 of them nailed down so far. These are the types we already discussed, so there's nothing novel here. Now, once we got them all in, what we notice is the flows that we have here, they're not ready to be concatenated, right? Because the types are not matching. So we need to add extra stages to divert the error path of these flows to our error sync, right? And this divert error stage that you can see we use twice in there is a flow that can be generically implemented and concatenated to all the stages that produce an either event with one of our errors, right? So we're going to see how that's done in a second. But if we assume that's available, we now have two flows that are capable of handling errors, right? So we can now, all the types are matching. So we can now go on and concatenate our stages using the via combinator. This is what we do in the bottom part of this code snippet. So the final sync ignore you see there is essentially because we are discarding the successfully stored AdWords changes here. This is because in this specific example, we wanted to keep it simple. Now, of course, you could just wire in one more sync to actually do something with these events. In this case, we just throw them away. So let's move back for a second to these divert error stages because we left it aside. So graphically, it's going to look like this. It's going to be a flow that ingests eithers. So either is something that can be either a left or a right, and where the left is usually identified as the error side, right? So here we ingest eithers. We just partition what comes in. If we have a left, we just pump it to a sink of choice. If we have a right, we emit it through the output port of the flow. So in the end, we have a flow, right? So how are we going to do it in code? So here's the equivalent in code. To get this done, we must use the graph DSL from Akka Streams. Now, the graph DSL, you probably heard about it if you've experimented with Akka Streams. It's a very powerful DSL that can essentially connect any stage in a very visual way. So what we need here is a partition stage, which is a fan-out stage that we create. And it takes a partitioner function. And this is used to decide which output ports to send whatever is presented as input. Now, then we need two more flows that we call left and right. And these are basically used to extract the values from the either in case it is a left or a right after the partition has happened. So finally, we can connect these stages using the squiggly arrow, whatever combinator of graph DSL. And this means connect the output port of a stage to the input port of the following stage. And as a last return statement, we expose the shape of our flow. And this means that our final shape, our final ports of the flow will be the input port of the partition stage that we created and the output port of the right-hand side, right? So a word of advice on graph DSL, as it does look tempting and it's cool. It's definitely very expressive, but we've noticed sometimes it's easy to get a bit overboard with it. So it shouldn't be used everywhere. That's the suggestion. It can end up damaging code readability because it carries boilerplate with it, of course, as you can see. Now, the suggestion is to use it wherever is needed, wherever you have no other choice. And this is essentially when you need fan in and fan out stage. Like in this case, we had a partition involved, so we needed to use it, right? But even then, it's good to limit its scope. So in this case, we limited the scope of this to this divert error stage, and that's now exposed as a flow, and we can use it in our graph without graph DSL, right? We can just go ahead using the normal fluent DSL, say, of Akka Streams. Now, the main temptation is to have a huge graph representing everything that goes on in your pipeline at a very fine-grained level, and that's very tempting because it can act as a live documentation, of course, and you can just send whoever's, trying to understand your code to that bit and say, okay, this is the pipeline. It's essentially live documentation, but it simply does not scale. So it can become messy very, very quickly. So you need to be a bit careful with it. So moving on here, we have identified a bunch of domain elements while designing our stages, right? So I've recapped them here in this slide. We've got events on the left-hand side, errors as well. We've got a few services that represent our business logic, to validate and store our data. Again, it's nice to reason in events here instead of entities. Now, finally, we need a place to manage the life cycle of our pipeline, right? So we still need things like failure handling, config management. We need to wire up the stages and run the stream and all that. So this layer will be our final application entry point, right? So very quickly, how it's going to look from a very simplistic point of view, this is how the code might look like. Configuration loading can happen in many, many flavors. For example, Scala community favorite is pure config, for instance. It allows to easily convert config files to strongly typed class hierarchy. Once we got a config object that we can obtain in whatever fashion you prefer, we can wire up our application by creating all the stages we need, right, up to the graph, and finally run it and obtain the materialized value out of the graph, which is all the handles we need. So using this approach, we end up modeling application config with a single case class here, right? So ideally, here we have one block per stage. And that's kind of neat, because we can now separate them and pass them down to the respective stage factory methods. Also, doing so, you end up with relatively organized config blocks, sections, that loosely corresponds to your stages. So this makes it easy to understand where to put your hands whenever you want to tune parts of your pipeline. So essentially, this completes our stack little framework here, in quotes. So we ended up essentially middle out. So we started by designing our reactive stages, so our graph and everything inside it, and let it drive the business layer, the domain layer, sorry, at the bottom, right? So note that this domain layer does not know about Akka Streams, about streaming or anything. It just provides, the business logic and the events definition. Now, the application layer on top as well wraps everything up by adding lifecycle management and essentially allows the application to be packaged and deployed and scaled wherever you want. So to quickly recap the key points here that we've touched on while taking this short journey, first, think about the stages that make up your pipeline. So you need to start simple and use composability to deal with complexity. It's also good to spend time designing the types of your stages. Make sure you make error handling and other side effects explicit, and use the materialized value to express control over your pipeline. Also, you should use events from your domain language to model the types of your pipeline. And thirdly, when you implement a stage, you got two possibilities. So either you find the stage off the shelf in a library and you adapt it to your domain types, or you have to provide the logic yourself, right? In this case, it's better to separate your business logic module from your streaming module for greater flexibility and testability, as we've seen. You can also go through these steps iteratively, maybe taking care of one stage at a time and build your pipeline progressively, which is always a good idea. So wrapping up, Akka Streams is a great piece of tech to build your reactive data pipelines. So the hope here is that you got a few useful ideas about how to think about your pipeline and come up with a sound plan to roll it out to production. So thank you very much for your time today. I'll be very happy to answer whatever question you might have, even later at the conference or at the handles that you see in the slide. Thank you.
Any questions?
Really nice talk. Thank you for that. I think it's the best one so far. I was curious about the publishing part. I've seen that you have a few, like 3 were mentioned as DSP, Google, Facebook. And from your presentation, basically you have a graph for each publisher. How would you scale to multiple publishers, like tens, for instance?
Thank you for your compliments first. So it's a great question. So essentially, that depends, of course, on what these what these advertisement platforms want. So as mentioned, they always need different data presented differently. So it's a bit of a challenge. So the key thing is to identify a common transformation that need to happen. That's common, basically, a common denominator that needs to happen while transforming the data before reaching this platform, and try and make that happen beforehand, before broadcasting out to them, and then maybe have like one further queue or a Kafka topic which you can put in between, and then from there you'll need to fan out and do whatever specific to these platforms in a bespoke mode. Now, the problem is that, again, every single one of them needs very different things, and it's not just HTTP calls as in this example. There are some of them which requires, for example, a file to be dropped, a CSV file to be dropped in an FTP bucket somewhere. So it's not exactly something you can do in the same way across the whole bunch. So it needs to be a bit bespoke.
Hi, thanks for your talk. Can you talk a little bit about unit testing, or 2-part question? Unit testing of Akka Streams, and then once you deploy in production, about monitoring of the system.
That's a great question, actually. Two great questions. So unit testing is was actually the fourth balls. The first ball you could see in the presentation there, but in the end I had to get it down. There's a whole lot to be discussed there as well. Essentially, it's good to structure your testing in a pyramid kind of way, like the classic approach that you could think about. It's very good to test stuff at the reactive stage level, because you could use, in this case, it's very easy using Akka Streams to produce fake stages you can connect to your real one when you're testing things, right? So it gives you, Akka Streams, it just not give you a test kit, it also gives you a way to very easily fake up stages to produce, for example, fake elements through your pipeline, or a sink to consume data and check what's going on. It's very easy to test things from a stage point of view, then of course from the whole stream point of view, where you can actually only do like eventually based testing or things like that, when you run everything and you just test whatever side effect happened from the outside. So this is one thing. The other thing that you mentioned was about monitoring, I believe. So essentially, if you follow what I said with the error handling approach, what's good to do about monitoring is actually treating events that you want to monitor the same way you would treat errors as well. So you can actually record whatever you want to monitor as an audit event and track it through your pipeline and send it to a sink of choice to actually handle it in whatever way you might seem proper. So it's the same exact pattern. If you keep this transparent, it's going to be way easier for you to understand what goes on in your pipeline.
Hey, do you have any tips for finding out what the bottleneck is in a graph? Because in our systems, we find that a lot of the times a particular flow becomes a bottleneck, and then we need to sort of increase the concurrency here, or like do this and that experiment. It takes a day or something to like figure out exactly where in the graph the thing is. And because of back pressure, everything slows down upstream as well. So you really can't tell exactly where the back pressure is really coming from. So do you have any tips?
Yeah. So yeah, I understand your what you're saying. That's one of the most difficult things that you might find yourself in. Now, again, if you maximize the configurability of your pipeline, exposing all the knobs, it's going to be fairly reasonably easy to to turn things and change numbers and see what happens in your pipeline. I guess you can, and because of back pressure, you can do that safely, right? So if everything is going slow and you don't have really, you can't really do worse than that. You can actually experiment with that even on a live system, right? So the first suggestion is try and expose as many knobs as you can from the outside, like this, all the parallelism and all that, to find out more. Of course, monitoring the pressure, like with valves and stuff across your flow, is also very important. So you actually have like a live visual of the rates that goes on in your graph.
Hey, so I'm curious how you would handle retries in the example that you put out. Like, let's say there was a read timeout from Kafka. Does that fall into the error flow, or would you put that somewhere else?
Retries, well, you would assume retries are something that follow like a catastrophic event, right? You wouldn't really, if you actually think about your error flows, you try and minimize, of course, anything that might happen and destroy your graph. But of course, you can envision like a retry policy in case something very, very bad happens. For example, you could have like a failure handling policy on your materializer and say, let us restart the whole thing in case there is a big problem. But that's something that needs to be infrequent. First of all, it needs to be something that's caused by something catastrophic, right? You need to, anything that is like an error that's expected, of course, you need to deal with it in the error handling path.
Cool, thank you.
Anyone else? That's it.
Thank you.